Okay, now let's do a directed aldol. Let's use the concepts from above and say, okay, when we're using that malonic ester, it was nice because we knew exactly how the reaction was going to happen because the pKa of the hydrogens in between the two carbonyls, the pKa of those hydrogens was so low, the base would react with that, and that would be the only thing the base would react with. So let's use that. We'll do a directed aldol where we take a very strong base. Instead of hydroxide, let's use our good buddy LDA, lithium diisopropylamide. And if we use LDA and THF, hey, we've seen this before. LDA, THF, sterically hindered strong base. If we had this ketone right here, note we had a sterically hindered carbon with its hydrogen here. So we've got a alpha carbon hydrogen here, two alpha carbon hydrogens here, more sterically hindered, less sterically hindered. LDA always attacks the less sterically hindered alpha hydrogen. So LDA will make this carbanion that we can attack this acetaldehyde carbonyl with, and aqueous workup will make this product right here. We have this CH3 is over here. Our original carbanion cyclohexanone is right here, and this acetaldehyde that got attacked, this carbonyl, CHO recall is aldehyde, this carbonyl becomes the OH, this CH3 is over there. Question, will this automatically dehydrate? Probably not, because we don't have any other conjugation. Might have to add a little extra base to get that to dehydrate. It might on its own, but we can stop it if we need to. We could stop it at this point if we needed to, because there's no extra conjugation. All right. Well, what if we did an intramolecular aldol? Check this out. What if instead of putting two ketones or aldehydes in there, what if we just start with one dicarbonyl compound, but give it enough space in between these two carbonyls that we can form a ring? So if we took this beast right here and we added base to it, one could say, okay, where are we going to form the carbanion? We know that carbonyl compounds with alpha hydrogens and base, we're going to form a carbanion. Could be here, could be here. Note, could be here and could be here, but since this is symmetrical here, we only get two possible carbanions, with the carbanion being on this carbon here, or this carbon here being the carbanion. Now, note, if this carbon is a carbanion here, since it is alpha to the carbonyl, it's can't attack this carbonyl. One could say it's already attached to it, so it's can't attack it. So this carbanion, if it's here, can only attack this carbonyl over here. Likewise, if this is the carbanion, it could only attack this carbonyl over here. It's already attached to that carbonyl. So these are two possibilities. Which way will it work? Well, the answer is this one. This OCH3 minus will take this carbon right here, which will make this the carbanion, and this carbanion will then come over and attack that carbonyl. Just keep track of your carbons. Realize if we're attacked, we're going to form a bond between this carbon and this carbon, which means we have 1, 2, 3, 4, 5 carbons in our ring. This will become a cyclopentane ring. Oh, but we'll have this carbonyl is still there. Nothing happened to this carbonyl. It'll be a cyclopentanone ring. And that's just keeping track of everything. Okay, here's carbon 1. It attacks this carbon, which note, that means carbon 1 is going to be bonded to the carbonyl carbon. And that carbonyl carbon, recall this becomes the OH in our Aldol reaction. And so carbon 5 will have an OH on it and a CH3. So carbon 1, carbon 2 is still the carbonyl. Carbon 1, carbon 2 is still the carbonyl. Carbon 3 is still CH2. Carbon 4 CH2. Carbon 5 used to be the carbonyl carbon. It has the OH and the CH3 on it. And then it is bonded back to carbon 1. And if a little dehydration, we can get the alpha-beta unsaturated carbonyl compound. And the question is, well, okay, that's good, but what would happen if this carbonyl gets attacked? or excuse me, if this alpha carbon gets attacked and take one of these hydrogens to make this carbanion. Well, if that happened, then the carbanion could only attack this carbonyl over here, giving us a 1, 2, 3, a 3-membered ring. We would get this beast, and hopefully this just looks awkward to you. Yeah, 3-membered rings, not nearly as stable. So this is an interesting question. At the first step here, which proton does the base attack? Does it attack this one, or does it attack this one over here? The true answer is, at the first step, both get attacked. On some molecules, one of these gets attacked. On some molecules, one of these gets attacked. Both sites will get attacked. The difference is, recall, that this equilibrium lies to the left. So no matter which one of these gets attacked, we don't get very much of this stuff here. If this far one gets attacked, then we form this compound. If this closer one here gets attacked, then we form this compound. It's still equilibrium, and since this is so much more stable than this is, if this occurs, this equilibrium will go back to the left, and if we're back here, then this equilibrium is also to the left, and so we're back where we started from. If this much less stable molecule is formed, the equilibrium pushes it to the left. If this molecule is formed, the equilibrium pushes it to the right, because this is a more stable molecule than that one is. So which one of these gets attacked? They both do, but only this carbanion will lead to product due to thermodynamics. So this is the only thing we will see. Cool. All right, and then comes Claisen. And Claisen said, okay, Aldol is getting all the rage these days, and we're dealing with aldehydes and ketones. Claisen says, what if we did esters? What if we did an Aldol reaction with esters? And I guess someone said, well, if we do an aldol reaction with esters, we can't call it an aldol because there's no alcohol, there's no aldehyde anymore. And so Claisen says, okay, well, let's call it Claisen. Actually, Claisen wasn't that way. Claisen just started doing the reactions with esters, and then everyone else called it, hey, let's do it with esters. Has anyone done that before? And someone said, yeah, Claisen's done that before. Okay, let's call these Claisen reactions. So a Claisen reaction, instead of 2 ketones or 2 aldehydes plus base, we're going to have 2 esters with base, which going to give us a beta keto ester. So let's take 2 of these esters right here. Note if we add base that the only hydrogen that gets snagged is one of these. We can only make a carbanion over here. This CH2 is not next to the carbonyl, so it's not going to react. It's this CH3, so we will only make the carbanion with this carbon over here. And so this guy will attack another one of itself. Here we go. So we make this base right here. This guy attacks another one of itself attacks the carbonyl to make an OH there. And that gives us our original ester. If we're following the pieces here, this CH3 is here. CH2 here. Here's our oxygen. Oops, I'm sorry, I'm in the wrong one. This CH3 is here. This CH2 is here. Here's our oxygen. Here's our carbonyl. Nothing happened to that carbonyl. Here's that CH2. It is now bonded to this carbon that used to be a carbonyl carbon, has an O- on it, and it has a methyl group on it, and it also has this alkoxy group on it, that's OCH2CH3. Note, though, from previous chapters that this is a leaving group. Esters are RCOZ compounds, which means once we have this negative charged oxygen up here, it can come back down, form the double bond, and kick off that group. Now this leads us to something interesting here, because if this ester gets kicked off, we now have all this is still in place. We have a CH2 here, our carbonyl. Now we have a beta dicarbonyl compound, and now we know that the pKa of these two hydrogens is back down to 9. They're in between two carbonyl carbons. pKa of 9 here. Our other product was ethoxide, strong base. So this ethoxide is going to come in and snag one of these hydrogens and make this carbanion. And we don't want that. So after this reaction is run for a bit, we've got some of this carbanion around. We add a little aqueous acid here to reprotonate that. So note, we have to, essentially what we're doing is we have to add acid to neutralize this strong base. It doesn't, turns out the acid doesn't actually neutralize a strong base, it just neutralizes the effects of the strong base. This strong base snags one of these hydrogens, and this acid puts the hydrogen back. All right. Well, if we do Clasons, let's do cross Clasons. Let's do that. Let's add two different esters. So if we do that, we can take, okay, we've got this carbonyl of our ester and ethoxy group on this side, phenyl group on this side, which means no hydrogens alpha to the carbonyl. Carbon here, no hydrogens, there's an oxygen. So this cannot be attacked by base. We cannot form the carbanion here. But this guy can. If we had this ester here, this ethyl acetate molecule here, adding base will change this into the carbanion, take away one of these three hydrogens, change this to the carbanion, we'll attack this carbonyl. Note, after this carbonyl gets attacked, forms the O-, comes back down, kicks off this ethyl OCH2CH3 group right there. So we end up with phenyl ring. This carbonyl reformed, this ethyl group got kicked off, but it now is bonded to this CH2, this carbonyl, and this ethoxide group right there, a beta keto ester. All right, so that's what will happen, our cross-Clason, if one ester has alpha hydrogens on it. What if we used a ketone and an ester? Okay, if we look at this, here's our ester, so we could attack one of these carbons one of these hydrogens right here, or we've got a ketone, we could attack one of these. If you remember from the last chapter when we were talking about the pKa's of these hydrogens that are alpha to carbonyls, recall that the pKa's of ketones, the hydrogens alpha to carbonyl of a ketone is about 19.2. Recall the pKa of esters is about 25 or so, which means if we put in base, we will only form the carbanion of the ketone. If you have a ketone and an ester mixed together, you put in base, only the only enolate that gets formed is of the ketone. Because these hydrogens have the lower pKa, they are more acidic. So then this negative carbanion will then attack this carbonyl carbon here, double bond breaks, double bond reforms, ethoxide kicked off, and we end up with our beta dicarbonyl compound. Okay. So let's look at this reaction here. What if we start with this ester, add the OCH2CH3-, let it come to equilibrium, and then throw in this beast right here. Look, this carbonyl with an ethoxy group on this side and an ethoxy group on the other side. Well, we let it come to equilibrium, which means we have some of this in solution, this carbanion. Let it attack this carbonyl, double bond breaks, double bond reforms, we got that leaving group, and then we've got, well, what do we got here? Let's see. We've got our ethyl group, our oxygen, our ethoxy group here, the carbonyl, this CH2, bonded to this, which is back to a carbonyl. One of the ethoxy groups is gone, but the other one is still there. We've got our malonic ester. So note, this is a way to generate a malonic ester, and then we can do our good old fun malonic ester synthesis from the previous chapter. Something to note, because this reaction goes so well and everything like that, you would probably not run this in the lab. If you needed malonic ester, you'd probably just buy it. Okay, well, what else could we do? Oh, let's check this out. Here's a cyclohexanol right here. Add base to form this carbanion, this enolate right here. And if we throw in this, check this out. It's ester on this side, acid chloride. That looks like a reactive molecule. Of course, what's the better leaving group? Ethoxide or chloride? Everyone at this point should probably be shouting chloride. Yeah, that's right. So if this carbon attacks that carbonyl, double bond breaks, double bond reforms, kicks off the better leaving group, chloride, to make this beta keto ester. All right. And real quick, the last reaction for this video, the Dieckmann reaction, is just an intramolecular Claisen to form 5 and 6 membered rings. Just like we had that intramolecular Aldol reaction, let's just start with 2 esters instead of 2 ketones or 2 aldehydes. 2 esters over here, and just add base. Note, the only carbanion that can be made is from one of these CH2s, or this CH2 over here, one of these two, but since this molecule is symmetrical, gives us the same thing on either side. Now someone's asking, well, what if the molecule was not symmetrical? Good point. If it wasn't a symmetrical molecule, you could probably get both carbanions possible. You'd have to look at both products, see which is the more stable product, and it might find out they're both reasonably stable, and you might get 2 possible products if both are reasonably stable. But for ease right now, let's have a symmetrical ester. You add the ethoxide, you got this, say this carbon, alpha to the carbonyl becomes the carbanion. It will attack this carbon. Double bond forms, breaks, double bond reforms, kicks off ethoxide here. Then it's just a matter of counting our carbons. Note this carbonyl is not going to be in the ring. It's 1, 2, 3, 4, 5, and this carbonyl will be in the ring. Recall, in an aldol, this would become an alcohol because there was no leaving group. In our Claisens and our Dieckmann, which is just an intramolecular Claisen, we've got the leaving group, so this stays as a carbonyl compound in the end. And so this carbon right here, carbon 5, is a carbonyl. It's the carbonyl of the ring. And this carbonyl is hanging off carbon 1, which is alpha to the carbonyl carbon of the ring.